NASA has released the first images taken by the James Webb Space Telescope.
The air feels electric, charged with the hum of realization that humanity has just peered deeper into its own beginning than ever before. Light, from a time when the universe was only a pale infant, has just whispered back from the furthest depths observed. The James Webb Space Telescope has laid bare the earliest known black hole nestled within an ancient, tiny, and dazzling little red dot galaxy, Kuiper's LRDZ-9, reaching back some 13 billion years to a universe barely half a billion years old. This is no ordinary cosmic find. It is a sight into the raw heart of creation itself, a primordial behemoth that defies our expectations. Before we start, smash the like and subscribe buttons for more updates. Astronomers following the light patterns from Kuiper's LRDZ-9 recognize the unmistakable signature of gas rapidly falling into an intense gravitational maw. What emerged was more astonishing. The central black hole is a titanic entity, approximately 38 million times the mass of the Sun, roughly 10 times greater than the supermassive black hole anchoring our own Milky Way. It commands about 5% of the host galaxy's stellar mass, a ratio that turns modern models upside down. The sheer density of surrounding gas shrouds the galaxy in a fiery red glow, likely redshifted by the abyss's voracious pull. This discovery reframes everything. It suggests that even when the universe was such a fledgling, black holes could already tower above expectations. This revelation is a cosmic jolt. If supermassive black holes existed so early, so massive, and so rapidly emerging, our theories about how they form must be fundamentally incomplete. Traditionally, supermassive black holes are thought to grow slowly, starting from light seeds, such as remnants of the first stars, merging and feeding over hundreds of millions of years. Yet here is one, born in under 500 million years, already gargantuan. That undermines the idea that black holes simply evolve slowly from small seeds through normal cosmic progression. This might mean that the earliest black holes either formed differently, perhaps as far more massive seeds to begin with, or enjoyed a growth spurt fueled by extreme conditions in the infant cosmos. The implications ripple outward. Seeing a black hole so massive so early demands re-evaluating not just black hole genesis but the birth of galaxies themselves. If galaxies could assemble, and their central engines could swell so fast, then cosmic structure may have matured with surprising speed. Such rapid assembly suggests the early universe wasn't a placid place. It was already dynamic, turbulent, and rich with gas flows powerful enough to fuel such monstrous growth. This challenges the delicate balance of cosmological models. Theories like hierarchical structure formation, in which small clumps coalesce into larger systems over vast spans, may need to account for bursts of furious formation, collisions, and runaway collapse. Understanding how Kuiper's LRDZ-9 even existed requires new simulations that allow for astonishingly efficient accretion, possibly aided by dense cosmic environments or unusually low angular momentum gas. Perhaps black hole birth in the early eras is more varied than assumed, a spectrum ranging from light seeds to direct collapse scenarios yielding heavy initial masses almost instantly. These findings expand the frontier of astronomical inquiry. Now, astronomers will scour JWS data for more little red dots, compact, bright red galaxies whose glow may conceal similarly ancient black holes. As more of these are discovered and characterized, a population may emerge, an early generation of massive black holes that dominated the universe from the start. This could reshape our timeline of cosmic dawn, pointing to an aggressive phase where seeds sprouted almost overnight. The red hue of such galaxies suggests dense cocooned environments, where gas is abundant yet veiled. That gas, funneling inward, may obscure the black hole but also feed it aggressively. If such environments were common in the first billion years, burgeoning black holes could have rapidly lit up the universe, carving deep changes into their surroundings by blasting out radiation and winds, perhaps influencing star formation and galaxy growth through energetic feedback. Our view into cosmic evolution grows richer and more disquieting. We once thought of early black holes as fragile, emerging slowly, but now we glimpse behemoths already grown. That alters our conception of early cosmology. It changes our map of the timeline of cosmic milestones. It raises the question, what else lurked unseen in those early eras? Could there be other astronomical phenomena? Quasars, massive protogalaxies, uncharted astrophysical mechanics, waiting just beyond current detection? Perhaps more dramatically, it reignites one of astronomy's oldest questions. How did supermassive black holes form? The discovery forces us to confront uncomfortable new possibilities. That current models are too conservative, too incremental. That nature's ambition in the early universe was grander, more urgent. We must now consider that massive direct collapse models might dominate, or that early black holes formed from exotic processes may be ultra-dense gas clouds collapsing under special conditions or collisions of massive star clusters feeding nascent black holes rapidly. The human dimension is equally powerful. Until now, supermassive black hole formation seemed esoteric and distant, but now we have a cosmic entity, a monstrous ancient creature, born when the universe was just 3% of its current age and already massive enough to dwarf early galaxies. This isn't a footnote in cosmic history. It's a revelation that challenges the narrative of formation, evolution, and the rhythm of cosmic time. In light of this, telescopes everywhere will turn their gaze to these LRDs. Spectroscopy, high-resolution imaging, multi-wavelength observations. They'll probe whether others host similar giants. Galactic archaeology now has a new frontier. Black holes that formed not gradually, but explosively, forever altering the landscape of early space. There is also the broader context. This discovery threads through grander narratives like the Hubble tension, cosmic background interpretation, and models of early universe star formation. Every element of cosmology, from dark matter distribution to baryonic physics, may need retuning if black holes can reach such mass so early. The delicate interplay of dark matter halos, gas cooling, star formation suppression, and black hole feedback must accommodate these fast-maturing giants. The universe, once perceived as a slow and steady builder, now appears occasionally raucous and hasty. Black holes could have forged themselves in a hurry, forging mechanical and radiative influences that sculpted their galaxies before stars ever settled into long lives. They might have been architects, not just products, of early cosmic order. From a philosophical angle, there is awe and dread intermingled. The discovery conjures an image, a primordial galaxy glowing red and fast collapsing, hosting a dark heart whose mass is unthinkable for its age. Light born in that era, mid-first billion years, now navigates 13 billion years of expansion to reach us. We stare, humbled, at a creature born when time itself was young. This find does not merely expand knowledge, it reshapes our narrative of cosmic history. It demands rewritten textbooks, fresh theories, new simulations. It sparks reimagination of everything from black hole seeds to galaxy assembly. It pushes us to ask, how many more cosmic surprises are hidden in Webb's data just beyond detection? What's clear is that the early universe was not a slow, orderly place. It was turbulent. It was violent. It hosted black holes of staggering mass that grew at unimaginable speed. And we've just glimpsed one, its existence a terrifying testament to the power of nature in its infancy. From here, every look at distant space gains new urgency. Are there others like Kuiper's LRDZ9? Could this be an outlier or the tip of an early universe iceberg veiled in red? The pursuit has begun. And in the pursuit lies the promise of new cosmic revelations. Dark, powerful, and unforgettable. The James Webb Space Telescope has not just made a discovery, it has ripped open a door onto a cosmic chapter we thought we understood, only to find it was vastly more dramatic, more extreme, and more mysterious than ever imagined. A sudden surge of excitement ripples through the astronomical community as the James Webb Space Telescope reveals MOM-Z14, a galaxy so distant and luminous that it appears to push the very boundary of human cosmic perception. Set more than 13.5 billion light-years away, its light traveling since the universe was only some 280 million years old, MOM-Z14 emerges as a bright, compact beacon amid the darkness of cosmic infancy. That a galaxy this early in cosmic history could shine so brightly, compact yet radiant, seems almost inconceivable. Its luminosity, powered by vigorous star formation and a near dust-free interstellar medium, floods Webb's sensors with ionizing photons and hints at a pace of creation far faster than imagined. As MOM-Z14 flickers on our screens, it reframes the narrative of the universe's formative years. Suddenly, the reionization epoch, once thought to be a slow, gradual transformation, is revealed as a time of astonishing activity. These early galaxies were not gentle seedlings. They were cosmic furnaces, forging stars with ferocious intensity, churning out photons that carved paths through the hydrogen fog of primordial space. The existence of MOM Z14 means that the universe's early chapters were more crowded and dynamic than we realized. Just when we think Webb has shown us the limit of cosmic extremes, Zhulong appears in the constellation of Sextans. This galaxy, observed at a redshift of 5.2, is a grand design spiral, a majestic Milky Way-like structure made of clearly defined arms, a quiet inner bulge, and vast star-forming regions. To see such an orderly and expansive galaxy only about 1.2 billion years post-Big Bang feels like stepping into a past that already holds the elegance of modern cosmic architecture. It suggests that under certain favorable conditions, galaxy formation didn't meander. It advanced rapidly enough to give rise to spiral structures while the universe was still young. Zhulong pushes the origins of galactic structure deeper into history, demanding explanations that account for both calm and chaos. Simultaneously, within the swirling chaos of galactic merger, the infinity galaxy emerges. Two ringed galaxies colliding in a cosmic dance shaped like an infinity symbol. In the fiery heart of this collision sits an active, supermassive black hole, dislocated from any galactic nucleus, forming directly in the turbulent zone between the two cores. This struck the core of theory because it suggests that in the chaos of collision, conditions can conspire to bypass conventional pathways entirely. Rather than a black hole growing slowly from small seeds, here a massive gas cloud collapsed directly, creating a heavy seed black hole over 1 million solar masses almost instantaneously. This discovery cleaves open the long-standing debate between light seed and heavy seed models of black hole formation, showing that nature may not be patient or incremental, but brutally efficient. As these wonders unfold, Webb probes closer to home. At the edge of the HD 181327 system, a band of icy bodies glints with water ice frozen in time. These icy remnants outline the outer architecture of a planetary system, offering clues about how planets form, perhaps from the cold outskirts inward, from frozen debris to rocky worlds. Webb's deep gaze thus touches on the origins of solar systems, and by extension the ingredients and geometry of worlds that might harbor life. Then comes the eerie possibility of planet in eclipse. Alpha Centauri A, our stellar neighbor, may be orbited by a giant Saturn-sized planet nestled in the habitable zone. Though tentative, since subsequent observations failed to spot it, this potential detection, if confirmed, would rewrite the story of our cosmic neighborhood, suggesting that even our closest system might hold hidden worlds. And there's TBUA 7b, newly discovered and entirely unforeseen, lurking enshrouded within a dusty disk around a young star. This Saturn-sized planet, one of the lightest ever detected, defied expectations. No telltale transit, no pre-detection hints, just a dim silhouette revealed by Webb's advanced coronagraph. It's a demonstration that planetary systems may be far more varied and elusive than models allow, and that the universe still hides countless surprises in its corners. At grand scale once more, Webb turned its gaze to a famed celestial landmark, the Hubble Ultra Deep Field, and plunged deeper. The MIRI Deep Imaging Survey revisited that patch of sky for nearly 100 hours, capturing more than 2,500 additional distant galaxies. Tiny, faint, and ancient, some dating to less than 1 billion years after the Big Bang. These new faces fill the gaps in our cosmic census, showing that the early universe brims with galaxies we had never seen, that even in regions once thought mapped, there lay hidden multitudes beyond reach. Another cosmic drama unfolds in the tragic spiral of a planet's final act, in an extraordinary event dubbed planetary suicide. JWST uncovered evidence of a Jupiter-sized planet spiraling into the outer layers of a star still in its main sequence. The concept of a living star consuming its own planet, not as a red giant at end of life but while still active, is both terrifying and surreal. It reveals that planetary systems can be unstable, dynamic, and sometimes self-destructive, shattering the assumption that planets once formed are destined to persist. All these revelations woven together paint a universe far more startling than we had dared to imagine. At each scale, from galaxies to spiral arms, from black holes to icy bodies, From exoplanet detection to planetary demise, the James Webb Space Telescope has shattered expectations. It has shown us that the early cosmos was fertile but frenzied, that structure could emerge with elegance amid chaos, that black holes could form swiftly and in strange places, that planetary systems can be elusive or doomed, and that the heavens we thought static are anything but. What emerges is a universe alive with urgency and complexity. Galaxies sprout grand designs in youth, mergers birth unexpected black holes, exoplanets hide or perish, surveys uncloak vast swarms of early galaxies. If the cosmos is a story, Webb is rewriting its pages daily. The implications ripple outward, far beyond academic journals. Our cosmic narrative, our origin story, is being rewritten. Educational charts, theoretical simulations, and science fiction alike will need new thinking. Philosophically, the universe becomes less a clockwork machine and more a roaring forge of creativity and violence. As the worlds shift before us, one thing is clear. The universe is not waiting. It's racing and rising, colliding and collapsing, revealing new marvels that challenge comprehension. And through it all, the James Webb Space Telescope stands as humanity's most audacious eye, surveying and unbinding the mysteries of creation. A sudden shiver runs through the astrophysical community when JWST reveals Uncover Z13, a ghostly Lyman break galaxy tucked within the gravitational embrace of the Abell 2744 supercluster. Counted among the oldest ever spotted, this spectral remnant hails from a time when the universe was scarcely more than 350 million years old, an embryonic era teeming with raw energy and unborn galaxies. Its light, bent and magnified by cosmic lensing, appears only as a faint whisper through the telescope's infrared gaze. Unlike any familiar star system, Uncover Z13 refuses comforting familiarity. It challenges expectations by existing at all, defying models that assume such structures needed time to form. Its ghostly presence is a silent scream. Creation was faster and harsher than anyone foresaw. A few pages further along in the cosmic ledger, JWST opens a window to the JADES GSZ14 Zero galaxy, a fiercely luminous titan from an epoch beneath 300 million years of cosmic history. This miniature colossus, compact yet heavy with 500 million solar masses, glows with the warmth of furious star formation. What sends ripples through theory is the detection of oxygen in this primordial world. Oxygen, a product of previous stellar generations, suggesting this galaxy matured chemically at an almost unimaginable pace. Elemental oxygen so soon after the Big Bang signals that the furnace of creation was not only blazing, but efficient, turning raw hydrogen into complex elements with disquieting rapidity. Shifting focus, the telescope turns toward a brown dwarf, often dismissed as a failed star, and finds something astonishing: methane emissions and probable aurorae dancing across its atmosphere. Such activity suggests the presence of an unseen partner, a hidden exomoon orbiting this substellar object, stirring its magnetic fields into spectral light shows. This too is unsettling. To think a moon, silent and unseen, could betray its existence through ethereal glow, hints at cosmic phenomena hiding just behind apparent emptiness. Elsewhere, Webb's instruments capture 14 Hercules C, a cold giant world gripped in an orbital struggle, looping through a chaotic, tilted path that defies smooth circular elegance. This exoplanet's orbit suggests a past of violent disruptions. Perhaps a companion star or rogue body tugged it into its misaligned trajectory. It's a portrait of instability and a reminder that planetary systems, even seemingly stable ones, can be shaped by unseen forces, leaving worlds spiraling on uncertain orbits. But arguably most petrifying is the JWST's discovery of planetary suicide, a Jupiter-sized planet spiraling inward to be consumed by a star that is still on the main sequence, still young and shining bright. The idea that a full-sized planet can be lost to the star's outer envelope, drawn in by tidal forces alone over eons, turns our notions of planetary permanence on their head. Far from passive celestial companions, planets may be mortal after all, doomed to vanish without fanfare even before their star's age. Each of these revelations, a hunted exomoon, the swift chemical maturity of ancient galaxies, the hidden chaos in orbital dynamics, planetary demise, threads together a cosmic narrative more unsettling than reassuring. They expose space not as a silent void, but as a stage of relentless change, where objects emerge, transform, and vanish with little warning. It's a universe that we thought we understood, a predictable clockwork construction, yet it turns out to be more like a symphony composed of unpredictable cadences. Galaxies mature rapidly through unanticipated chemical evolution. Planets waltz into chaos or twilight spiral into stellar graves. Hidden companions reveal themselves not through sight but through ethereal interplays of light. JWS forces us to rethink the timeline of cosmic evolution. That galaxies such as Jade's GSZ 14-0 could house oxygen signifies that stellar generations were already pushing chemistry forward mere hundreds of millions of years after the Big Bang. That exomoons and solitary planets might play hide-and-seek with our instruments challenges how we hunt for distant worlds. That a planet could literally vanish into its sun expands risk beyond the usual catastrophic catastrophes we imagine. Looking ahead, these findings don't merely update our astronomical textbooks. They rewrite them. Simulations of planetary system dynamics must now account for death through starvation or orbital decay, not just collisions or stellar expansion. Models of galaxy formation must account for chemical maturation so early that the ingredients for life might emerge faster than expected. Search strategies for exoplanets must adapt to hunt beneath starlight's glare or find the auroral whispers of moons long unseen. At the human level, the emotional weight is profound. Each faint signal, from a ghostly galaxy to an inflamed exoplanet, carries the memory of events billions of years old. Light that embarked on its journey close to the dawn of time reaches our eyes now. Ferrying forbidden secrets of creation and destruction, triumph and disappearance. That a planet could vanish without stellar fireworks, or that cosmic chemistry could erupt so soon, speaks of a universe far more capricious, volatile, and breathtaking than we ever imagined. These revelations form a new cosmic lexicon. We shift from a universe that matures slowly to one that can race through epochs. From stable planetary systems to ones in quiet chaos, from dark inert bodies to auroral dancers that hint at unseen worlds, from slow chemical evolution to immediate complexity. The universe is alive, it is turbulent, it is surprising, and it is often terrifying in that sublime way only vast emptiness can be. Within that, the James Webb Space Telescope emerges not as a passive observer but as a storyteller. It brings us fragments of a reality that doesn't bow to expectation. It forces us to confront cosmic truths that are beautiful, strange, and unstoppable. In the face of such revelations, we glimpse our own fragility. Earth appears more rare, more precious, subject to forces that may be common elsewhere, revealed only through the whisper of infrared light crossing time. The cosmos is creative and indifferent, capable of forging complexity within cosmic moments and dissolving planets without notice. And in that indifference lies both awe and unease. Stepping back, it's clear. JWS isn't just a telescope, it's the herald of cosmic disquiet. It pulls back veils and forces us to stare deeper into the universe's mysteries, many of which defy explanation, but all of which expand our realization of how small and how extraordinary our place truly is. As the telescope continues to peer outward, what remains is the question, not just what we will see next, but how we will adapt, philosophically and scientifically, when the universe refuses to conform to our expectations. The James Webb Space Telescope, still in its early operational years, pivots its gaze to a sector of sky unremarkable in visible light, but rich in potential when scanned in infrared. What emerges is a sprawling chain of proto-galaxies strung together like luminous beads, stretching across millions of light years. This cosmic filament, frozen in its early developmental stage, offers a direct glimpse at the scaffolding of the universe. Rather than the isolated clumps that traditional simulations suggest, these structures reveal a tightly woven web already forming when the cosmos was less than 1 billion years old. It is a living snapshot of the universe in the act of assembling itself, a revelation that the large-scale architecture we see today may have taken shape far earlier than anticipated. Within one of these filaments lies an anomaly, a compact galaxy radiating energy from a single hyper-concentrated region. Webb's spectroscopic analysis shows the unmistakable fingerprints of population 3 stars, hypothetical for decades but now potentially observed. These stars, forged entirely from pristine hydrogen and helium, burn hotter and live shorter lives than any stars that came after. If confirmed, this detection would be the first observational evidence of the universe's very first stellar generation. Their presence at this stage tells us that even while the cosmic web was still being spun, the first lights had already ignited and perished, enriching their surroundings with the first metals. Shifting to a different cosmic frontier, Webb focuses on the heart of a galaxy cluster 5 billion light-years away and discovers a gravitational lens unlike any seen before. Instead of a single distorted arc, the light of a background galaxy has been stretched into an intricate spiral pattern, a cosmic vortex of light created by an unusual alignment of multiple massive objects along our line of sight. This natural magnifying glass provides an unprecedented boost in resolution, allowing astronomers to study a galaxy that would otherwise be far too distant and faint. The vortex lens not only offers a new tool for probing deep space, but also challenges existing models of how mass is distributed within galaxy clusters. Closer to home, Webb trains its instruments on the faint glow of a white dwarf system just 100 light-years away. Around this stellar remnant, a ring of debris betrays the violent past of planetary destruction. Infrared signatures suggest the debris is rich in water-bearing minerals, remnants of a once oceanic world now pulverized by tidal forces. The discovery indicates that water-rich planets may be more common than previously assumed, and that their destruction can preserve chemical evidence long after the worlds themselves are gone. This finding adds weight to the idea that the ingredients for habitability might be widespread, scattered like cosmic seeds even in systems long past their prime. Webb's capacity to dissect planetary atmospheres also brings forward an unexpected candidate for study, a super-Earth orbiting an orange dwarf star 40 light-years away. Atmospheric readings reveal a dense mix of hydrogen, helium, and photochemically produced hazes. Most startling is the tentative detection of dimethyl sulfide, a molecule that on Earth is produced almost entirely by marine microorganisms. While no one is declaring life, the presence of such a compound in an alien atmosphere forces a careful re-evaluation of biosignature criteria and highlights the telescope's sensitivity to even faint molecular traces. Moving outward once again, Webb's deep field programs reveal a massive stellar nursery inside a dwarf galaxy at the edge of the observable universe. Unlike the sprawling, loosely organized nebulae of our own galaxy, this nursery is a dense knot of gas and dust forming stars at a rate dozens of times faster than the Milky Way's busiest regions. Such efficiency raises questions about the environmental factors: pressure, turbulence, magnetic fields that can drive such explosive star birth. It also implies that early dwarf galaxies may have been far more important to cosmic reionization than current theories credit. In an entirely different corner of the sky, Webb isolates a quasar so luminous that it briefly outshines its host galaxy by a factor of 1,000. Detailed analysis suggests the supermassive black hole powering it is accreting matter at close to the theoretical maximum rate. Any faster, and radiation pressure would blow material away. What's remarkable is the quasar's age. It exists at a time when its black hole should have been too young to grow this large by conventional means. This observation reinforces the emerging narrative that the universe's first billion years saw black holes grow by mechanisms still poorly understood, perhaps through direct collapse or repeated mergers in dense environments. Even more intriguing is the detection of a faint extended halo of light surrounding this quasar, visible only in the deepest infrared exposures. This halo could be the earliest example of quasar-driven feedback. Energetic outflows heating and expelling gas from the galaxy, regulating both its own growth and that of its stars. The interplay between such powerful outflows and the delicate process of star formation is now seen not as a late-stage phenomenon, but as a formative force operating from the universe's infancy. Webb also peers into the turbulent heart of a stellar merger within our own galaxy, catching the event in its mid-stage. Two massive stars spiraling ever closer have already thrown off vast shells of gas and dust, creating a complex lattice of glowing arcs. Shockwaves from colliding winds are triggering bursts of new star formation in the surrounding molecular clouds. This rare, close-up look at a merger in progress offers a living laboratory for understanding how such cataclysms can seed their surroundings with both destruction and creation. In the far reaches beyond the Milky Way, the telescope catches a glimpse of an intergalactic rogue, a massive planet drifting without a parent star. Measuring roughly 3 times Jupiter's mass, it floats in the darkness between galaxies, perhaps ejected from its birth system by gravitational chaos. Its isolation is punctuated by a faint, warm glow, enough for Webb to detect traces of a thick atmosphere composed primarily of hydrogen and ammonia. This wandering giant challenges the assumption that planets form and live out their lives bound to stars. Instead, it suggests that the galaxyless void may be littered with orphan worlds. Webb's sensitivity uncovers a subtle, diffuse glow between galaxies in a rich cluster, light from countless stars not bound to any galaxy, stripped away by tidal interactions over billions of years. This intra-cluster light, faint and ancient, is a record of galactic cannibalism and cosmic recycling, the byproduct of a slow dance of mergers and destruction. By studying its properties, astronomers can reconstruct the violent histories of galaxy clusters and trace the fate of stars long divorced from their birthplaces. In each of these cases, the James Webb Space Telescope doesn't merely add data points, it expands the very frame in which we imagine the universe. It shows that structure forms earlier, chemistry advances faster, violence shapes systems more profoundly, and the inventory of cosmic objects is stranger than we dared guess. Every observation is a reminder that the universe's history is not a straight path of gradual change, but a chaotic tapestry woven from threads of creation and annihilation, subtlety and spectacle, darkness and light. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on Webb's terrifying discovery? What do you expect will happen? We want to hear from you. Thank you for watching, and see you next time.